A vector describes both magnitude and direction, and magnitude is a number. So a vector can model all kinds of things, including force in physics, or electromagnetism, like an electric field or magnet field, or I think maybe it's a lot easier to just think about wind. So there are two links that are shown here. I clicked on the second one, and at the current moment, um, at the time of recording, it's just to kind of zoom in somewhere. It looks like there's some, activity of this kind that we don't like to see in the southeast of the country, but you can really see sort of a visual representation of wind, and you see, for instance, like over here, just to the east of, well, I don't know where this is, Maine or something like this. You see the direction of the wind being towards the southwest mostly, and then you see sort of at least the way they're trying to show you magnitude here is, I think, by either color or maybe the length of the line segments. They're trying to do something to try to depict places where there's more wind versus less wind. So I'm not sure I'm putting the right words to it, but over here it looks like there's a lot of wind, whereas somewhere in the kind of middle of the country where we are here in Wisconsin, it just at the moment that I'm recording this, doesn't happen to be all that windy. That's the way I would interpret what's going on in this website. Okay, in math, using vectors allows us to algebraically describe three-dimensional geometry. And the thing is, drawing in 3D can be hard. So we use vectors like this, 6, 7, 8, in angle brackets as a record-keeping tool. All this vector really is, it just holds on to three numbers. That's all it is. The first number is 6, the second number is 7, and the third number is 8. Manipulating vectors algebraically is sort of like drawing without having to draw. It's drawing without drawing. But for this to work, we actually need to understand how vector arithmetic and vector algebra are connected to vector geometry. So each thing that we do in vector land, which looks more algebraic and just is kind of real easy in working with the symbols, working with basic arithmetic like 6 plus 2, we need to understand what that means in the geometric setting. Otherwise, we're not really drawing without drawing. So just keep in mind a vector has both magnitude and direction, which way an arrow points. I should step back. One way to represent a vector is to draw. We'll draw an arrow, and which direction the arrow points is the direction in the sense of direction up here, and then the length of the arrow drawn will represent the magnitude. So for instance, here are three vectors, and I've drawn the vectors in bold. So U and V are different vectors, but I intentionally do them to be the same magnitude. I hope the computer is representing these correctly. If you used a sheet of paper to measure how long this is on screen and how long V is, I hope it's correct. It might be off by a little due to some aspect ratio issues with the recording, but U and V are intended to be the same magnitude or length, just in different directions. V and W, on the other hand, are also different vectors, and the reason is, while they share the same direction, they have different magnitude. So imagine the vector W representing more wind in the same direction. So, an hour later, it's just windier, but the wind is blowing in the same direction as before. So 2D vectors you can draw on the xy plane. This tends to be fairly easy to do. For a vector, location does not technically matter. So all 6 of the blue arrows here represent the same vector. There is one of these that starts at the origin. That's the one that we're going to call the position vector. So even though these are all technically considered equal vectors, sometimes we actually do care about the location of the vector. And in that case, the vector that we have that starts at the origin, we'll call that a position vector. It's easier to talk about 2D vectors, it's easier to draw them, but all the concepts apply exactly the way you'd expect in three-dimensional space. By the way, let's go back to these vectors, these special kind of vectors that start at the origin. They, again, are called position vectors. And there's a complete correspondence between position vectors and points in the plane. So every point in the plane will correspond to a position vector. It's really just, so I've done the point information in red and the vector information in blue. So the point is just the point, right? And it's written using parentheses. For this class, we are going to use standard kind of ordered pair with parentheses for points. And in this class, we're going to use angle brackets for the vectors. Now, if you're taking linear algebra at the same time, or you have in the past, maybe in your linear algebra class, you're using a different notation for vector. You're going to have to deal with that. It'll be okay. But I think for right now, to try to communicate that points and vectors should be thought of as different, they are different concepts. I'd like to ensure that we are strict and are using different notation. So the point is this, that infinitesimally small single location, whereas the position vector is the vector that starts at the point, which is the origin, and ends at the point here that we're talking about here, drawn in red. Okay, so the vector is the arrow in blue, whereas the point is just the red dot. Let's put it that way. Okay, so the point P here is the point -1, 2, that ordered pair with x coordinate -1 and y coordinate 2. V is the vector from the origin to that point P. And here are some other notations for it. So we can use a bold V. That's what the book does. We can, on paper, writing in bold is hard, but I really want you to, I insist on it, in fact, in terms of points on things like quizzes and homeworks and so on, to make sure that you draw perhaps your standard V, but draw an arrow above. And we can describe this vector as being defined in this case as the point, as the vector that starts at the origin, that point, and ends at the point P. So we'll draw an arrow over the 2 to mean that. And when a position vector ends at this point, like in this example, -1, 2, then we'll use those same numbers. We'll borrow the coordinates of the point and make them the components of the vector. So this vector V has first component -1 and second component 2, or x component -1 and y component 2. So just some terminology and convention, terminology and notation convention matters. So for a vector, we're going to say component instead of coordinate. If you're a little lackadaisical about this, or I am, I think it's going to be okay. But just to try to at least to start, I'm going to try to stick with coordinates to describe the individual numbers in a point, and components to describe the individual numbers in a vector. For a vector, we'll draw in bold, or it's easier to just draw with a little arrow above. For a vector, we're going to use angle brackets when we're writing it in this notation. Parentheses will be used for points. Okay, another way to describe a vector, and we already kind of hinted at it with the position vector, but you could do this with any 2 points. So specify point A, specify point B. You got to start with 2 points, and the vector starts at point A and ends at point B. So for example, I have the point 1, 2 in red, called that A. I have the point 7, 5 in red, called that B. So the points are in red, these 2 separate points, and then the vector V, I will define it here to be the vector that starts at the point A and ends at the point B. So by the way, we can draw that same vector. By same vector, I mean same direction and same magnitude, starting at the origin. And I just shifted, I made the computer take this blue arrow and I shifted it to be located at the origin. So I hope the tilt, or the slope in a sense, is the same as before. By the way, what point is this? Maybe pause and figure out for yourself. What point should this be? It's not going to be 7, 5 anymore. Things had to shift a little bit. Can you figure it out? Okay, that point should be 6, 3, right? Because if you look, to get from A to B, you've got to move 6 units to the right, and you have to move 3 units up. I hope that looks fair to you. Where did the 6 come from? If we wanted to create a little more of a recipe, perhaps notice that 6 equals 7 minus 1. And then where did the 3 come from? This 3 right here. You could say, oh, to create a recipe, to create a procedure for that, shouldn't that be the y coordinate of V minus the y coordinate of A? Notice the subtraction is perhaps not in the order that you might have thought of, but it is what it is to make the vector point in the direction it needs to. So based on this example, we'll say this: given the points A and B, with A being x1, y1, and B being x2, y2, the vector V that starts at A and ends at B should in component form be v1, v2, where v1 is really x2 minus x1, and v2 is y2 minus y1. So on your own, go back to the previous example and check that this formula works. More specifically, check that the first guess, everyone's first guess is incorrect. To take the information, to get the x component, we often want to take the x coordinate of the starting point and then subtract the x coordinate of the ending point. But it's got to be in reverse, right? So the way you originally think it ought to work, it just doesn't work. And just draw the pictures to just convince yourself. So you should always take the terminal point, or the ending point's coordinate, and then subtract the initial point's coordinate, not the other way around. So on your own, I would suggest drawing 2 points, C and D, so that the vector W, defined as starting at C and ending at D, drawn as a position vector,
so that that vector points in the fourth quadrant. So think of how you would have to organize your 2 points C and D. Where do they need to be located relative to each other so that the vector starting at C, ending at D would point towards the fourth quadrant? Then verify that the formula works. In other words, you need to make sure, if that's the direction that the vector is pointing, that the first component is positive and the second component is negative. And once you've tried these on your own activities, especially the second on your own activity, I did create an app, and you can verify that everything works completely as you expect using this app. Now in 3D, all the same concepts occur. It's just harder to draw. That's all that really happens here. So I'd like to draw in the point 1, 2, 4. So what I did is on the x-axis I moved 1 unit over, on the y-axis I moved 2 units over. There's this point right here where the circle is kind of where I'm honing in on using my mouse. Right there, that point where the mouse currently is 1, 2, 0. So I've got to go 4 units up from there. Okay, then I'll draw the point B as 10, 3, 3, meaning 10 units along the x-axis, 3 units along the y-axis. There's this point that's on the floor, as I like to call it, where z is equal to 0. So this is 10, 3, 0, but we're going to move 3 units up from there. So this point point B is actually 1 unit below, in terms of floor level, point A. Now, of course, it's also just below in the depiction, but had we looked at this picture from a different vantage point, B could certainly appear higher on the page than A, but in reality, it has a smaller Z coordinate. So all of these oddities about drawing are just a little unfortunate. But we'll draw a vector. Sorry if the arrowhead is kind of hard to see here, but the vector starts at point A, ends at point B. And the formula works exactly the way you'd expect, right? So we should do the final point's x-coordinate minus the initial point's x-coordinate. So 10 minus 1. That's how we get this 9 here. And if we continue this all the way through, for the third coordinate, let's say for the third component, we should take B's third coordinate, namely a 3, and then subtract A's Z coordinate, which is a 4. So 3 minus 4, we get negative 1. And I hope that negative 1 really makes sense. I'm using this example to illustrate. I already just had mentioned that the point A is really on a higher floor level than the point B. So doesn't it make sense that the vector that starts at A and ends at B should have a negative third component?